Welcome back to Each 370. In this video, we're going to be going through the Project 4 Spec example. And so I'm going to assume before we start that you've already watched lectures through the lecture on direct map caches. You've watched all the labs through the cache lab, and then you've also read over the Project 4 Spec. So let's go ahead and get started. So before we get into the actual example, I do want to point out some of the features of the starter code. The starter code is very open to change. You have a lot of design choices because the output doesn't directly translate to the starter structs that we give you, unlike other projects such as Project 1S and Project 3, where the states that we give you correspond directly to what the output looks like. In this project, we're not going to actually check your cache contents. We're just going to check the messages passed in between the cache and the processor and memory. And so there are multiple ways to configure your cache, but we'll go through what we've provided so far. So speaking of the messages that we'll track, all the output in this project is going to be based on what we call these print actions. And so you have 5 possible print actions for a writeback writeback allocate on store cache. And so we'll have a cache to processor. That is where you get a hit of some sort in the cache and you transfer the data to the processor upon a load. We have a processor to cache. That is where you find the data in the cache and you write to it. So it only happened for store instructions. So I guess to recap, the cache to processor, that is only for loads and instruction fetches. Then we have the processor to cache, which is only for store instructions. And then the other 3 could happen as a result of any access to the cache. So if we are going from memory to cache, that means we had some sort of miss, and we need to transfer what is not in the cache to the cache. And so that could happen on load, and it could also happen on store because we have an allocate on write type cache. Could also happen on fetch. We also have cache to memory. That is where we are evicting a dirty block. And so that could happen again on load, fetch, or store, but it has to happen for a block that has some sort of previous store. So if a block has not had a store since it was last brought into the cache, then it'll be clean. And we would use the other print action on eviction, which would be a cache to nowhere. So these last 3 can occur anywhere, but under certain conditions. And so these will only happen on misses. The first 2 will happen on both hits and misses. All right. By the way, do not touch these. I would recommend. Do not also touch the print action function, since that works as we have designed it. Really, most of the design choice that you have is within the statistics function and within the initialization of the cache, as well as the actual cache struct itself. And let's move on. This is the block struct that we have provided for you. And so it has really 2 main parts. It has the data, which we might remember from the lab, is the actual stuff that is from memory. And then we have all these other things that are really overhead. Technically, the set isn't stored in a real hardware cache, so that might be considered some amount of extra. But all the other things are overhead that has to be present in a writeback cache. And so that would include the dirty bit, the valid bit, the LRU label, which you have a lot of leeway on to decide what exactly that means, and then the tag. If you feel like you need to add anything else, you can definitely do that. But all of this down below the data would be considered overhead. And then the cache struct itself is made up of a whole bunch of those blocks. And so if you partition out your blocks, you can come up with any sort of cache configuration. So for example, if I have an array of just 4 blocks in a fully associative cache, I could use all of them to belong to the same set. In a direct map cache, I could have each one be its own set, or in some set associative cache, I could divide them up into different chunks to belong to different sets. That is one way to do it. You can also use the explicit set variable that we've provided in the block struct. It's up to you. But in real hardware, we would probably do the partitioning scheme, except it would be more automatic. All right. This depicts how your code is going to flow. And this project is unique in that we are working on really two separate components. And one of them is already finished for us. That is our simulator.c file. This is from project 1S. And so you have a couple options with this project. You can use your own and make certain modifications. And so check the spec. But some of those modifications would be to call the cache init function once at the beginning of your program, and then to call the print stats function once at the end of your program. And then all of your memory accesses, so anything referencing state.mem within your main project 1S loop and not in the initialization, you'll replace that with a cache access. And then the cache access will do the things to see if it's in the cache, and if necessary, make a couple of memory accesses. And those memory accesses will be able to come back to project 1S and access state.mem. So the cache won't directly access state.mem. Your main loop in your project 1S file will not access state.mem. Really only the initialization, where we read in the machine code file, set all the other addresses to 0, and then this mem access function. Those will be the only two parts that actually touch state.mem. So just to recap, cache init will be called once at the beginning. Print stats will also be called once at the end. And then cache access will be called many times, depending on what the machine code is telling the processor to do. And so at least at every fetch and load and store. And so those will become the three sources of our address references. Now, one hint, make sure to treat instruction fetches from the perspective of your cache the exact same as a load. Even though they're going to appear in two different places within your main while loop, you can treat them the exact same. It's only stores that you will treat slightly differently. All right, let us move on now. One other thing before I move on, you can also use the instructor provided Project 1S simulator. We provide it as an object file. And if you remember from Project 2L, an object file is compiled assembly code or compiled machine code. And so you won't be able to access the C file if you are going to use the instructor version. But because of linking, we can take some cache C file, compile it to an object file, and then link it with another object file to get our final executable. And that will be your actual cache simulator. And so we do this because it speeds up compilation. We only have to compile the simulator once into an object file. And then from there, every time we make an edit to the cache, we don't have to recompile the whole thing. And also, we do not want to freely give out the instructor solution to Project 1S, but you are still free to use yours. And it would look a little something like this. The optional part would add in your C file up here, which you can choose to compile once or compile over and over again, depending on how well it is working. And so you can trust that ours is working, even if yours isn't. So if you're having struggles trying to figure out how things go, you can use ours, but it might be trickier to debug. If you want to debug, you won't be able to look inside the simulator, but you can set breakpoints in cache init and cache access and print stats to see what is going on and run your debugger as normal. So let's actually get into the spec example. Now, all of the tests for Project 4 will be named in a particular scheme, and the name will specify what our cache setup is going to be, because different assembly code files might produce different cache behavior depending on the actual parameters of the cache. So whenever you make a test name, you'll have some name and then dot, and then you'll have a block size in words. And so that is going to be 4 for the spec example. And then you'll have a number of sets. And so that's going to be 2 here. And then you'll have a blocks per set. And then you'll have your regular extension AS or S or LC2K. And so for the spec example, we're going to work with a block size of 4, 2 sets, and 1 block per set. And one thing to note, if you ever see 1 block per set, that means that we're working with a direct mapped cache. On the flip side, if you ever see only 1 set, that means that we're working with a fully associative cache. And so I guess there is a possibility that you could have both a direct map and a fully associative cache. Really, in that case, it would just be kind of like a temporary variable or a buffer instead. With any other parameters, though, that means that we're going to be working with a set associative cache. In order to understand those, make sure to watch the set associative cache lecture. So this is a direct map cache, and since it's direct mapped, we can ignore LRU. However, if you write your LRU to work for set associative caches, then it'll work the exact same for direct map caches and fully associative caches. So one of the keys to this project is to generalize to the set associative, because a fully associative and a direct map cache are each types of set associative caches. And so this image here represents what our overhead will be in total. So we can map this blue section to the data portion here, and then we can map all this overhead to the other things that we see in this image. The valid bit, the dirty bit, the LRU, which isn't used in the direct map, and then the tag. So now let's look at the actual code. It disappeared. So the assembly code program that we've given you for this example is very simple. It's only 4 instructions. And I want to point out a couple peculiarities with it first. The first is that we are accessing addresses that aren't necessarily in our machine code range. So for example, the very first instruction accesses address 6 because we take register A, which is 0, plus constant 6, and we get address 6. So the very first element that we'll be modifying is right here. And it will start off as 0. And in Project 1S, we wouldn't see that in our print state. However, we have modified the mem access function for this project so that it'll make sure that it'll print out anything that is written to. So that means that anything it doesn't print, you can assume is still just 0 within the memory. Now, depending on your stores, it might still have some other value in the cache, but it would be 0 in memory until it is printed out. And so we'll see that as we go through the output in the end. Same goes for address 23 and 30. Those will start off as 0. Those will actually remain 0 because we're only loading from them and not storing to them. And so they might not appear in our print state, but we can trust that they are in memory and they start off as 0, as is convention in LC2K. So the question that I think trips up most students who are starting this project is how our cache is laid out with a particular aspect. And one of the things to know about our cache is that, like memory in LC2K, which is von Neumann, it will hold both instructions and data. So that means that when we are first running any program, our first address access will always be to 0 because our PC starts at 0, and we would always, in our Project 1S simulator, access state.mem at PC. So now, instead of accessing state.mem directly, we'll go through the cache, and the cache will always find that it is a miss on the very first cache access. So we will also bring in PC 0 from memory. And so we'll see this kind of alternating behavior. We'll do an instruction fetch, and then we might do a load in a store. We'll do another instruction fetch, maybe another load in store, and we'll go back and forth, and we will see more cache accesses from fetches than anything else. So let's look at the simulation for that first access. So that first access is to address 0. And that is to fetch the actual machine code. And so we're going to give this machine code to the processor, to our Project 1S portion, so that the processor knows what exactly to execute. And so that will include the machine code for the SW. It'll see that it's an SW. It'll add register A plus offset, but it can't do that until we give it the correct machine code. So if we were to just give it a 0, it would be incorrect. And so whenever you see a return in your cache access, make sure that you're returning actual data. Because if we just give the processor something that is invalid, then it will not produce the correct behavior. So we know that our cache has 2 sets. We know that the block size is 4 words. And so on this very first access to address 0, we're going to access the entire block that contains 0. And because the block size is 4 and 0 itself is divisible by 4, we can start at 0 and count 1, 2, 3, 4 words. And then all of those will be loaded as a block into our cache over here. And so that means that we will change our valid bit to a 1. This is only a fetch. It's not a store. So we'll keep our dirty bit at 0, and then we will get the appropriate tag. Now, remember that all blocks, or sorry, all addresses within the same block share a tag and a set index. They only differ in the block offset. And so we can see this in the different columns of this table over here. They all have tags of 0. They all have set indexes of 0, but the block offsets range from 0 to 3. And so we will move them all around as a unit. We will update our tag in the cache, and then we will be able to move on after returning the actual machine code for the store instruction. And so from that, we would get a couple actions. First, we would print out that we are transferring the entire block that contains this machine code from memory to the cache. So that is from addresses 0 to 3, because that makes up this very first block. And then we need to actually get the machine code to the processor. And so we will transfer that from the cache. One thing to note, we're not going to transfer all of what we just brought in the block to the cache. We're going to transfer a block, a big chunk, from memory to cache, and then we will transfer a word, a much smaller chunk, to the actual processor. We don't need to transfer 0 to 3 from the cache to processor. And so we will see only 0 to 3 go from memory to cache, and 0 to 0 go from the cache to processor. That brings up a generalization that you can follow with this project. Whenever you see a cache to processor or a processor to cache, you should see only one word being transferred. But when you see something from memory to cache, or cache to memory, or cache to nowhere, you should see an entire block size load. So since our block size is 4, we see 4 addresses in the range here. And then here, when we're going to the processor, we just have 1 word that is being transferred. So now our processor will actually interpret the instruction. We will add register A, which is 0 plus 6. And so we know that we will next be storing register 1, which will start off with the value 0. We'll be storing that to address 6. So when we get to that in our cache, we will first look through our existing cache, and we need to figure out if that address is present in the cache. So looking through it, we know that if we were to take 6, and 6 in binary is a bunch of zeros, and then we have 1, 1, 0. So our last 2 bits would be our block offset. We know that because the log base 2 of 4 is 2. And then we would look at 1 bit of set index, and we know that because the log base 2 of 2 is 1. And so this here is our number of sets, and the 4 here is our block size. So we can see that we're looking for tag 0 within set number 1. And set number 1 right now is invalid. So we have nothing in there. We will get a miss. And because we are doing an allocate on write policy, we will need to bring the block containing address 6 into the cache first. That'll be our very first thing that we do. And so that will include addresses 4 through 7. We know that because all of those, once again, share the same tag, which is 0, and the same set index, which is 1. And so the quick and easy way I like to do it, I know my block size is 4, so I go down in my address from 6 until I find an address that is a multiple of 4. So if I go down from 6, 5, 4, I see that 4 is a multiple of 4. And then I will start there to bring in my 4 words that will define this block. And so they'll all start off as zeros. So we'll bring in these 4 zeros into the cache, and then we will overwrite address 6, which is block offset 2, with the new data, which also happens to be a 0. So we'll bring in zeros, overwrite one of them with another 0. And then we have to mark this block as dirty because we have now stored to it. Now, in theory, you could make some optimization where you don't mark it dirty because you're not actually changing the data. We will not be doing that for this project. We're just going to see if it's a store and mark that. There are various reasons for doing that. Oftentimes, if we try to put that computation in the cache itself, we get more complicated logic, and our access time for the cache becomes longer. So that is not something that is typically done out in the real world, and so we won't be doing it for this project either. But now this block is dirty. It has a tag of 0 inside of set 1. And so this will produce these 2 print actions. Because our set 1 was empty, we didn't have to evict anything whenever we got that miss. And so then we brought in the words 4 through 7 from memory to the cache. And so once again, we know that 4 through 7, that has a range of size, block size. And then we transferred 6, 6, which is just one word, from the processor to the cache. So before we had cache to processor with word 0, and now it's just word 6 from processor to the cache because we're doing a store. Let's move on to the next instruction. Next, our PC will increment to 1. So our PC is now 1. And then we have to fetch the machine code for the instruction at PC1. Now, breaking out the address, we can see that this binary address here is address 1. Our block offset will be 1, our set index will be 0, and our tag will be 0. And so if we look into our cache, we find tag 0 within set 0, and we see that it's valid. So that means that we will have a hit for the first time in this example. And so we can immediately index into the data block with our block offset and return that to the project 1S portion. And so we don't have anything to transfer from or to memory or out of the cache. So we will just transfer this single word from the cache to processor, and then we will decode it and continue to execute it. Now this LW will be accessing address 23, because note that our registers 0 and 1 still contain value 0, and we are loading register A plus offset, so 0 plus 23 is 0. And so we will be loading that into register 1. Now, conceptually, we know that address 23 still has a 0, so the actual contents of register 1 won't change, but we'll still load that into the register. So let's look. First, we have to see if 23 exists in our cache. So 23 in binary, let's see, that's 16 plus 4 plus 2 plus 1. So I get a 1, 0, 1, 1, 1. So that means that my tag right here becomes 2. And here are all the leading zeros for it. Our set will be 1, and our block offset will be 3. So if I look in set 1, I see that my tag of 0 that currently exists in the cache does not match my tag of 2 that I'm looking for. So I'm going to get a miss. And so that means that I have to make room for this block that contains 23. So first we are going to be evicting this block in set 1 that has a tag of 0. And we will remember from before that at least contained address 6. We'll actually remember that that contained addresses 4 through 7. So that's the block that we will be evicting here. Now, because it is dirty, we will have to write back each of these blocks, or sorry, each of these words in this block back to memory. And so that is because our dirty bit is allocated on a block size granularity. We're not tracking dirtiness per word within a block. We are just tracking if the entire block is dirty. So that means that we will write back the entire block to the cache. And so our next print action, I'll skip ahead for a second, will be transferring 4 through 7 from the cache to the memory. So this is a dirty eviction. So now it's out, and we need to bring the block containing 23. Once again, we can work down from 23 into our next multiple of 4. That would be 20. So that's where we will start from. So we will bring 20 through 23 into the cache. And of course, these are still all zeros. So our actual cache data would have all zeros for now. That might not always be the case, especially if you've written something or you're actually accessing something in the data section of your program with the dot fills. But for now, they are all zeros. And so we will bring that block from memory to the cache. And then finally, we will actually transfer the fetched word, which is number 23, from the cache to the processor. Now our output looks like this. Let us move on. Now our PC will once again increment to 2. PC is now 2. And we remember that our set 0 still has addresses 0 through 3. So we will actually get a hit. And so that will be pretty simple, but it's the same thing as before. We check the valid bit in set 0. We check the tag to make sure it matches our expected tag of 0. And then we can index directly into that and return the machine code for LW0130. Now we will decode the LW0130 and execute it and then access memory. So our address will once again be 30. And once again, we have to break that down into the tag, set, and block offset. So 30 in binary is 16 plus 8 plus 4 plus 2, and then I guess plus 0. So if we break it up, we will have a tag of 3, a set of 1, once again, and then a block offset of 2. So we'll go into set 1, which is just this block. We will check the valid bit and the tag to make sure that the valid is a 1 and the tag matches. In this case, it doesn't. So we're going to get another miss, which means that we need to evict the existing block in set 1. Remember that that contained 20 through 23. So we will have to evict all of those. Now, because our dirty bit is 0, this is not a dirty block. And so we don't have to write back to memory. We're just going to kick it out. And the reason we can do that is because the cache state of this block and the memory state are exactly identical. We know that for certain. And so we can just throw away the data from the cache because we know that a backup is in memory. So we'll evict it and bring in the block containing 30. Once again, we can work down to our next power of or multiple of 4, which would be 28. So we will load 28 through 31 to define this block. And so we will once again do the eviction, bring in the new data. They'll all start as zeros because we haven't modified anything in that block, and it's not in our initial .fill section. And so then our output will look like this. We'll have this cache to nowhere. That's the throwaway part. Then we'll have a memory to cache once again, and then we will transfer word 30 from the cache to the processor to fill the load and place that value into register 1, because that is register B in the LW. So now, just to recap, our cache looks like this. We still have the machine code for addresses 0 through 3 in set 0, and then we have addresses 28 through 31 in our other set. So now let's move on to the last instruction. This is a halt. Our PC will increment to 3 before we fetch the halt. And so that halt is at address 3. Same deal as before, we can break it down into the tag set and block offset. Well, we will remember that that is 0, 0, and 3. And so we will check set 0, because that is our set index. We'll check the valid bit. It is a 1. And then we'll check the tag to match. And it does match, because it's equal to the one we're looking for, which is 0. So we can index directly into it. We've gotten a hit, and we can return the machine code for the halt to the processor. And once the processor receives that, it will be done. And so our program is over. And so now just a couple cleanup things. We will have all of our print actions printed out. And I actually don't have the rest of the output in these slides that needs to be printed, but we will also print the final state and the number of memory accesses. I'll show you real quick how to calculate those. But first, let's just go over all of our print actions once again. So we had a couple of memory to cache. So that would be here, 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 and here. So that's a total of 4 memory to cache actions. We had just one cache to memory action. That's because we had one store and we evicted the block with that one store. And then everything else was either cache to processor or processor to cache. And so I've highlighted in red the print actions that resulted from our machine code, our fetches, that is. And so we only had 4 words of machine code, so they all fit in a block, and we were able to keep them in the cache the entire time. We never had to evict any of our instructions. So that means that we just had that initial memory to cache, and then we had 4 subsequent cache to processor actions. And all the others in white were actually handling the loads and stores from our program. So this first section here was transferring or was working to get address 6. And then we had the actions for address 23. And then we had the actions for address 30. So, all right, data accesses in this particular program ended up being a lot more costly in terms of things for the cache to do. Now, like I said, we will print out the final state. The final state is the same as Project 1S with one exception. This will contain the actual contents of DRAM up until either the highest address that was present in our machine code, our input to the simulator, or the highest address that we wrote to. So the highest address that we wrote to whenever we were evicting that dirty block from the cache would have been address 7. So our final state would print out memory through 7. And because we were only working with zeros after these the machine code for these 4 instructions, we should see just all zeros. And remember that anything that isn't printed out is still 0. So we haven't actually really changed anything with this project. Also note the only register we modified was register 1. And by the end, we still loaded the value 0 into register 1. So at the end of this particular program, all the registers would contain just 0. But our PC would be 4, because that is 1 after the PC for the halt instruction. So our PCs go 0, 1, 2, 3. And then that would be our final state. So our final state for this, we would have registers, all zeros, our memory, we'd have our machine code, then zeros, and for our PC, we would have 4. After the final state, we will also print out the number of memory accesses made. And so all this means is the number of times that you should call the mem access function, which we will remember is available to the cache even though it sits in the simulator portion. So it is a global function over in the simulator part, and so it can be called by the cache part even though it is compiled in the object file. And so every time we get a cache miss, we should be loading in all of the words for the block that we missed on through this memory access function. So at least for the 4 print actions that I've dotted here, we should call mem access 4 times. 4 times because that's the block size. Also, whenever we are writing to memory, that is when we are evicting a dirty block, we should be calling memory access for each of those words that we write back. And so we would call it 4 more times there. We would not call it for cache to nowhere because we shouldn't actually be accessing memory whenever we do a cache to nowhere, because that's inefficient. It incurs unnecessary writes to the memory. And so in total, we see 5 print actions that interacted with memory. Each of those will call mem access for every word in the block. And so we'll get a total of 20. That is 5, your number, times your block size, which is 4 memory accesses. So in that case, it'd be 20. And that is everything I have for this project example. Good luck on the project, and make sure to post on Piazza if you have any questions.